You know, in math, we spend so much time learning formulas that move us forward, from a question to an answer, from point A to point B. But what happens when you've already got the answer, and you need to figure out what the original question was? Well, today, we're going to see why sometimes the most powerful move you can make isn't going forward, it's knowing how to work in reverse.
To really get what I'm talking about, we're going to start with a real-world problem. A very, down-to-earth one, you could say. Let's talk about a big old cone of gravel. So, picture this. You're running a landscaping business. You sell gravel, and you pile it up in these big cones. And you know the shape is always the same. The height is always exactly twice the radius. This nice, consistent relationship means we can cook up a pretty slick formula.
And here it is, the formula that powers our business. Think of it as a machine that only goes one way. You pop in the radius of the cone, you turn the crank, and boom, out comes the total volume. It works perfectly every single time. But what happens when the problem comes at you from the other direction? All of a sudden, our perfect little formula feels, well, kinda useless, doesn't it? We know the volume, the output of our machine, and we need to find the radius, the input. Our one-way machine just isn't built for this. We need to figure out how to run it in reverse.
And that is where this absolutely brilliant mathematical concept comes into play. What we need is an undo button for our formula. We need its inverse.
At its core, the idea is actually way simpler than it sounds. An inverse function, which we write as f with a little -1, does exactly what you think it does. It takes the output from your original function and tells you the exact input that made it. It literally just reverses the whole process.
The best way to think about it is like a recipe. The original function is the recipe for baking a cake. You put in your ingredients, that's the input, and you get a cake, the output. The inverse function, that's like a magic unbaking recipe. You put the cake in, and it tells you the exact ingredients that went into it. All it does is swap the roles of input and output. Simple as that.
But of course, just when we think we've found the perfect tool, we hit a snag, a little complication. It turns out this super powerful undo button doesn't work on every single function out there. There's a rule we have to follow.
Let's take a look at one of the most famous functions in the book, the simple parabola, y equals x squared. This function, for our purposes right now, is a bit of a problem child. Why? Because if we try to reverse it, we run into a kind of identity crisis.
The problem becomes crystal clear with something called the horizontal line test. Look at that parabola. If you just draw a straight horizontal line across it, say at y equals 4, where does it hit the graph? Well, it hits it in two different spots, at x equals 2 and all the way over at x equals -2. So if our output is 4, what was the input? Was it 2 or was it -2? The path backward isn't clear. It's ambiguous. And this really gets to the heart of the rule. For a function to have a trustworthy inverse, it has to be 1-to-1. That just means every output comes from one and only one input. Our parabola fails this test big time. So, does that mean we're just stuck? No way. Mathematicians are way too clever for that. There's a breakthrough, a really simple and elegant way to get around this problem and basically make our function play by the rules. Okay, check this out. This is the aha moment. What if we just make a choice? What if we decide to just ignore half of the parabola? Let's say we're only interested in the right side, where all the x values are positive. Now, does our horizontal line hit it more than once? Nope. By restricting the domain, which is just the set of inputs, we've created a brand new, well-behaved function that is 1-to-1. And now, it can have an inverse. And once you've got a 1-to-1 function, finding the inverse is just a straightforward 3-step recipe. First, just to make things easier, you replace f of x with y. Then, and this is the key move, you literally swap the places of x and y. I mean, that makes sense, right? We're swapping the input and the output. And finally, you just do the algebra to solve for your new y. And that new equation, that's your inverse function.
And here is the absolutely beautiful result of that process. On the left, there's our restricted parabola, and on the right, that's its inverse. And do you notice how it's a perfect reflection across that diagonal line, y equals x? It's like a perfect mirror image. This is always what happens, and it's just so visually satisfying.
And what's so cool is that by finding the inverse of our x squared function, we've actually created a whole new type of function. We call these radical functions because they involve a root. In this case, a square root. This connection is fundamental. The inverse of a quadratic is a square root function. They're two sides of the same coin. So after that whole journey through the theory, it is finally time for the payoff. We started with a real-world problem, we discovered this idea of an inverse, we navigated a tricky complication, and we even found a new type of function. Now, let's put it all together and go back to that cone of gravel. Okay, so our original formula was for volume. By using our three-step process, we found its inverse, which gives us the radius. So now we can finally answer our customer's question. We plug in the volume they want, 100 cubic feet, into our new inverse function, and out pops the answer, a radius of about 3.63 feet. Problem solved. That's the power of working backward. But the real payoff, the big takeaway here, is realizing that this isn't just a neat trick for landscaping. This ability to reverse functions and the radical functions that we get from them are absolutely critical in tons of fields.
I mean, just look at engineering. The speed of a dragster isn't some simple linear thing. It's modeled by a cube root function. And that actually makes sense physically. If you double the horsepower, you don't double your top speed. The gains start to shrink as you go faster. And if you want to figure out how much horsepower you need to hit a certain speed, well, you'd need the inverse of this function.
And these things are just everywhere once you start looking. Oceanographers use radical functions to connect the speed of its tsunami to how deep the ocean is. Doctors use them to calculate body surface area for medicine dosages. Economists use them, financial planners, electrical engineers. It is a surprisingly universal tool.
So when you really think about it, the path we took was pretty amazing. We started with the simple need to go in reverse. That one idea forced us to come up with a mathematical undo button, which in turn led us to a whole new class of functions, these radical functions, that help us model everything from race cars to tidal waves. All of that came from just asking, hey, how do we get back to where we started?
So that leaves you with a final thought to chew on. Think about your daily life. The time it takes to fill a bathtub based on how far the faucet is open. The brightness of a light bulb based on the dimmer switch. What's a process you understand forwards? And what new insights might you discover if you thought about its inverse?